welcome back to my YouTube channel. In this video, I am going to discuss about Ampere's circuital theorem for NEET and JEE exam. Okay, from the Oersted principle, we got that current carrying conductor produces magnetic field. Okay, Biot-Savart's law gives the magnitude. There is another scientist, Ampere. He was introduced a relation. He said that the line integral of magnetic field around a closed loop is equal to mu 0 times net current enclosed in that loop. That is, you see that closed integral of B dot dl is equal to mu 0 times net current enclosed in that. Okay, how much is the current enclosed in that loop? Okay, then by using Ampere's circuital theorem, we can find out the magnetic field produced by a current carrying conductor. Okay, so to apply the Ampere's circuital theorem, we have to choose a closed loop. That closed loop is called as Amperian loop. Okay, that Amperian loop may tangential to all the point with B, or B is normal all the point in that loop, and the third case B may 0 or B may vanishes in that loop. Okay, based on these three situations we can choose. Okay, now we will see how we can apply the Ampere's circuital theorem. Okay, so we are taking a case, magnetic field due to a long wire. Long wire means it is an infinitely long wire. Okay, so you see this is an infinitely long wire. It carries a current I. Okay, so we need to find out the magnetic field at a point B, which is r distance from it. Okay, to apply the Ampere's circuital theorem, we have to see the nature of the loop, nature of the magnetic field. Based on that, we can choose the Ampere loop. Okay, then so the magnetic field produced by the current carrying conductor is found out by right hand thumb rule. So I apply the right hand thumb rule, place the thumb in the direction of current, curl the fingers magnetic field. So you can see that here it is going into it, here it is coming out. So this is a magnetic field direction. Okay, that means the magnetic field due to a straight current carrying conductor is a concentric circle. Is a concentric circle. So we can choose the Amperian loop based on that. Okay, so the Amperian loop now we can choose like this. Okay, like a circle. I choose the Amperian loop, and in that Amperian loop I choose a small portion, that is dl. Okay, so now we can find out integral B dot dl. Okay, integral B dot dl is equal to B dl cos how much? The magnetic field is a concentric circle, so the loop is also circle, so the theta is 0 because magnetic field is tangential. Okay, so we will get it as integral B dl unit. Okay, so what about the current enclosed? Only I. Okay, so here B is, you can take it outside, integral dl into mu 0 I. What about the integration of dl? That is B into the total circumference of the circle you will get, that is 2 pi r, that is equal to mu 0 I you will get. Okay, then now you see the B is equal to mu 0 I divided by 2 pi r. This is the magnetic field due to a infinitely long straight current carrying conductor. Okay, the direction of the conductor can be found out by right hand thumb rule. Okay, then next we will see the magnetic field due to a solenoid. The magnetic field due to a solenoid. What about the magnetic field due to a solenoid? What is solenoid? Solenoid is a long wire is wound in the form of a ellipse. Okay, in such a way that the circles are to be placed closer. Okay, so this is the axis of the solenoid. So we are consider the magnetic field here and magnetic field here is 0 because outside the solenoid the magnetic field is non-uniform and very smaller. So these two things we are consider the magnetic field is 0. Only the magnetic field is at here. Okay. So magnetic field at a point inside the solenoid is mu 0 Ni. What is N? N is the number of turns per unit length. If L is the length of the solenoid, we can write like this. Okay. Then the direction of the magnetic field produced by a solenoid can be found out by using right hand rule. Okay. Curl your palm in the direction of current, then the thumb gives the magnetic field direction. Okay. Next we will see the magnetic field due to a toroid. Magnetic field due to a toroid. Okay. Toroid means the solenoid is turned in the form of a circle like this. Okay, so if you take it as a thing, here if you consider as a point inside this, here the magnetic field is 0. Here also the magnetic field is 0. Only the magnetic field is present inside the solenoid. Okay, inside the open space is 0. Outside the toroid also magnetic field is 0. Inside the solenoid, magnetic field at a point inside the solenoid is mu 0 Ni. Here N is the number of turns per unit length. If R is the radius, number of turns per unit length is 2 pi R. Clear? Okay. This is the magnetic field due to toroid and solenoid. Now we will see magnetic field due to a cylindrical wire. Cylindrical long wire. So I consider cylindrical wire. This is a cylindrical wire having the radius A. Okay. The consideration is this is infinitely long and the current is uniformly distributed through this wire. Okay. Current is uniformly distributed through this wire. That means current per unit area is constant. Entire portion in the wire. Okay. Then first of all we need to find out the magnetic field in different cases. The first case, what we are going to take, this is the first case. The first case is the magnetic field due to a point that is the R is less than a, you look at here like this you put. Okay, like this you put. Okay, so you have to choose the ambient loop based on that. Okay, clear? Okay. So if the R is less than the radius, the magnetic field B value is B is equal to mu 0 I by 2 pi A square into R. That is the magnetic field is directly proportional to R. Okay. Then the case 2. If R is equal to A, the magnetic field is mu 0 I by 2 pi A you will get. Okay. And case 3. If R is greater than the radius, so you will get as B is equal to mu 0 I by 2 pi R you will get. That is the magnetic field is inversely proportional to distance here. Okay, so we can draw the variation of magnetic field with the distance. That is here B in the y axis, R in the x axis. Okay, up to A. What about the variation? You see that directly proportional. Okay, so from 0 to R, it is B is directly proportional to R. Okay, then after that, this is the maximum value. Again, it will be inversely proportional. So the variation is like this. So here in this portions, B is inversely proportional. Okay, clear? This is about the theories of Ampere circuital theorem. Now we will go to the problems. The type 1 problem. Uniform hollow conducting cylinder carries uniform current density. Which is the best graph shows the variation of B with the radial distance R. Okay, this is a hollow cylindrical conductor. It having inner radius is R by 2 and outer radius is R is given. Okay, so uniform current density in this region, they given the variation of B with the R. So many graphs are given. Which is the best graph we have to choose? Okay, clear? Then so this is a hollow cylinder. That means there is no current is to be there in this region, only in this region. Okay. What about the inner radius? Inner radius is R by 2. This radius is R by 2 and outer radius is R. Okay. And the current is uniformly distributed. That is, current density is constant. What about the current density? I by A. What about the area? Area is how much? That is area of cross section. That is pi R square minus pi R square by 4. This is the current density. This is the current per unit area. Okay. Now we will discuss the different cases. First, we will consider the radial distance. The R is less than R by 2. If R is less than R by 2, what about the magnetic field? That is the first case. Okay. So that means the point is here, like this it will come. If this is the axis, the point is like this. Okay. If the point is like this, what about, is there any magnetic field is here? There is no magnetic field is here. So here in this region, B is equal to 0. Okay, clear? The next case, R by 2 less than R less than R by 2 less than or equal to R less than or equal to R. That means in this region. Now the point is where? In between this. Okay, I consider the point is here like this. Okay, clear. So we have to apply the Ampere circuital theorem and we have to find out the magnetic field. Okay, so to apply the Ampere circuital theorem, we have to know the nature of the magnetic field. The magnetic field nature can be found out by right hand thumb rule. Okay, because here it is a straight conductor. So you see this. The magnetic field is like a concentric circle. So I am going to imagine a Amperian loop is a circle. Okay, Amperian loop is a circle of radius R. Okay, so what about integral B dot dl? Okay, here you see that B integral B dl cos 0 you will get, because magnetic field is a concentric circle and the loop also concentric circle. So if you consider a portion, small portion dl, the angle is to be 0. Okay, so that is equal to integral B dl. Okay, then what is the integration of B dl? You get integration of B dl is B into integration of dl. That is how much you will get? B into, what about integration of dl? That is the circumference of this circle, that is 2 pi r you will get. Okay, then this is equal to mu 0 into I enclosed. What about mu 0 into I enclosed? I enclosed is equal to J is the current density, that is the current per unit area into the given area. That means from here to this region only. Okay, so we can write that is pi into capital R square minus pi into small r square. Okay, this is the thing about it. Sorry, now that this loop is inside it, so we have to change like that. This is my mistake. So mu 0 in closer is equal to mu 0 into j into, sorry, in this region. Okay, clear. So what you will get, that is mu 0 into pi r square minus pi r square by 4 you will get. Okay, this is the answer. Okay, now you can apply this. So B, Ampere's circuital theorem you can apply. So what you will get, B into 2 pi r is equal to mu 0 into j into pi r square minus pi into capital R square by 4. Okay, clear? Then now you see, what about the B value? You will get B is equal to mu 0 j divided by 2 pi r into pi r square minus pi r square by 4. This 2 pi you multiply inside, what you will get, mu 0 j into pi into r square divided by 2 pi r minus pi into capital R square divided by 2 pi r. That is, this 2 also we can take it outside, divided by 2. Okay, then 4 pi r you will get. Okay, clear? Now you can divide with this pi r and this. So what you will get, that is B is equal to mu 0 j divided by 2 into, what you will get, that is r minus pi is to be cancelled. So capital R square divided by 4 r you will get. Okay, this is a magnetic field in which region? In between r by 2 and a small r. Okay, clear? Then now we will going to find out the magnetic field at a point is outside the cylinder. Okay, that means I am consider now the point is here. This is the point. So what about the magnetic field? That is, we can apply that the condition is r is greater than or equal to r. Okay, so we have to choose the Amperian loop like this. There is a big Amperian loop. So we can say that integral B dl, that is B dl cos 0 that is equal to mu 0 into in closed. Okay, so we can choose this. You see this? I am going to choose the Amperian loop that is like this. Okay, this is the Amperian loop. This is the radius r. This is the point P. Okay, clear? So the current enclosed is the total current, that is I. Total current I. Okay, then that is integral B dl is equal to what you will get, B into integration of dl into mu 0 into I. Okay, integration of dl is equal to 2 pi r. So B is equal to what you will get, B is equal to mu 0 I by 2 pi r you will get. Okay, if small r is equal to capital R, what you will get, B is equal to mu 0 I by 2 pi into capital R. Okay, we can choose this also. Okay, clear? This is a variation here, or equal to also the same variation. Clear? Now which one is the best option? This is not possible, because here you see that it is after r, it is inversely proportional, but there is no straight portion, is not there. In between r by 2r, the magnetic field is not a constant. You see that it is to be dependent upon r. Okay, so these two are not possible. Okay, then next you see about this. This is also not be possible, because the magnetic field may change to, you see that, change to 0. Okay, after this, after r by 2, what is that? Or after r by 2, magnetic field is 0. Then it is to be slowly increasing. Okay, it is slowly increasing, not suddenly increases from a particular value. Okay, so this is the best graph. Okay, this is the best graph. Clear? Okay, then this is about type 1. Now we will see type 2. A long straight wire of radius A carries a steady current I The current is uniformly distributed across a cross section. The ratio of the man field due to A by 2 and A is. Okay, so we already know a formula. Magnetic field due to a cylindrical wire at which the current is uniformly distributed. The formula is B is equal to mu 0 I divided by 2 pi A square into R. Okay, if R is less than A, okay, then mu 0 I by 2 pi A when R is equal to R, and mu 0 I by 2 pi R when R is greater than A. Okay, this is the formula. By using this you can find out it. Okay, then first of all we need to find out the man field in the A by 2 ratio. Okay, A by 2 radius. Okay, so that means R is equal to A by 2. If R is equal to A by 2, that is the radius is there given as A, so it is less than. So which equation? This equation we use, that is B1 like that I am taking, that is mu 0 I divided by 2 pi into radius, that is A here, so A square into R, instead of R, A by 2. Okay, clear? So next, what about this here? We can cancel it and we can write down mu 0 I by 4 pi A, like that we can write. Okay, this is the B1 value. Okay, now the next case, if R is equal to 2A, that means where is the point? If R is equal to 2A means it is outside the cylindrical conductor. So this is the thing. Okay, so B is equal to mu 0 I by 2 pi R. R value is 2A, so into 2A. So we will get it as B2 is equal to mu 0 I by 4 pi E. So look at here, they are asking to find out the ratio. The B1 by B2, what you will get? These two are same in magnitude, 1 you will get. Okay, this is about type 2. Now we will see type 3. Magnetic field at a point inside a infinitely long straight thin walled pipe. Okay, we need to find out magnetic field inside a thin walled pipe. Okay, so this is a thin walled pipe I consider. Okay, this is the axis of the pipe. A point P is inside it. Okay, so I am going to imagine an Ampere loop like this. Okay, so what is Ampere's circuital theorem? Integral B dot dl is equal to mu 0 I. You look at this loop. Is there any current is enclosed? Only through this thin wall only current is to be flowing. So there is no current enclosed. So this we will get it as 0. Okay, so magnetic field inside a thin wall pipe is 0. Clear? Okay, this is about type 3. Now type 4. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per unit length is half, what about the new magnetic field? Okay, so a long solenoid magnetic field formula is B is equal to mu 0 Ni. Okay, now the new magnetic field, that is equal to mu 0 into this N value, what is it is changed by half and I is to be doubled. So what you will get? Mu 0, this 2 and 2 cancel, mu 0 Ni you will get. That is new value of magnetic field is equal to the old value. Okay, this is about type 4.
Thank you for watching the video. Please subscribe my channel. If you like this video, please put like and share.